Okay, good evening, everyone. Hello, my name is Rafael Palacios. I am the head of the Department of Aeronautics, and it's an honor and a privilege to welcome you all today to the inaugural of Professor Oliver Buxton. I would like to welcome as well all people that we have online. We are streamlining the event, and of course all the guests that came to Imperial today to be with us and honor Oliver. Just in case, to start, I need to tell you that in the event of a fire alarm, it's a rear fire. Therefore, please follow the emergency exit signs to leave the lecture theater. The assembly point is on the corner of Exhibition Road and Imperial College Road. Virtual attendees, please take note, you are welcome to ask questions during the Q&A during the chat. So we'll be monitoring that, and at the end of the lecture, we can take those questions back. And I would like to, of course, say a few words about Oli. I got his CV here. I would like to highlight a few of the issues. A few of the story behind Oliver. He joined Imperial as a PhD the same year as joined an academic. So 2007 is an important year for the two of us. So he came from a degree in engineering at Cambridge and St. John's College. And he was doing a PhD here until 2011 with Professor Bharat Ganapati Ramani, which is with us today. After that, he went to do a postdoctoral research fellow to the University of Texas at Austin, and then came in 2013 when he joined Imperial as a lecturer. He was promoted to senior lecturer in 2017, reader 2021, and professor of fluid mechanics from last year. He has a fantastic career so far. He got an ERCA grant, which is the most prestigious award in Europe right now. He was a fellow of the EPSRC, the Engineering and Physical Science Research College Council, until next year. He got the Da Vinci Award for his PhD. He is currently a fellow of the Royal Aeronautical Society. He led the Pilot Center for the European Research Community on Flow, Turbulence and Combustion in the UK. Advisory board of the UK Turbulence Consortium, 17 PhD students, which I assume many of them may be here today, 5 postdocs, 50 plus papers, 1 NASA technical report, 13 book chapters, and the list goes on. So it's a real honor and a privilege to have you in our team, Oliver, and the floor is yours. Looking forward to your talk.
Okay, thank you very much, Rafa, and thank you to all of you for making it here today. It's a real privilege to be able to give this lecture in front of all of you from all walks of life, or my life specifically. Okay, so first of all, we need some background. So the question is, what is turbulence and where is it? And when people discover that I research turbulence, their first question is to say how annoying it is when they're flying through it in an aircraft. But in fact, turbulence is everywhere, and I would argue it's one of the most important problems in the universe. So, for example, in a star, the convective layer is turbulent, and this affects things like the lifetime of a star and the amount of radiation that it produces. The Earth has a turbulent inner core, which contains liquid iron. This produces a magnetic field, which we can see when we look at the northern lights, for example. This magnetic field shields our atmosphere from charged particles from the sun, which prevents the atmosphere from being stripped, which is a fate that befell Mars. So perhaps without turbulence, there would be no atmosphere. And as we'll see later in the lecture, turbulence plays a very important role in governing rainfall and precipitation in clouds, and of course, without fresh water, there would be no life. And it can also quite literally kill you, as I can attest when I opened my undergraduate turbulence exam. But in this case, I'm going to talk about the flow in an aorta, for example. So if we have a turbulent flow in the heart, we can damage the aorta or coronary blood vessels. This can lead to a buildup of plaque formation, and of course, if this is swept away and blocks a blood vessel, we can have a fatal heart attack. So it's a very important problem, and it's not just through aircraft that we encounter it. Now, that explains where turbulence is, but the next question is, what is turbulence? And like a particular genre of literature, there is no strict definition, but we know it when we see it. But it has some key features which we might want to talk about. So it's chaotic, it's beautiful, so we can see it's been a muse for some fantastic artists like Da Vinci and Van Gogh, who have both captured it with exceptional detail, in fact. Its study was born in Manchester in the late 19th century, which is obviously a bonus as well. But importantly, we can see that it contains multiple length and timescales, which makes it a very rich and interesting problem. It's also a problem of fluid mechanics, which means it's governed by this equation, which is known as the Navier-Stokes equation. And they literally build supercomputers because of the existence of this equation, because it's non-linear, which means it admits chaotic solutions, and it's also non-local. So this you might have come across with the butterfly effect, where people talk about a butterfly flapping its wings in Brazil, causing a hurricane in Texas. But importantly, and we're going to come back to this later in the lecture, it's vortical, which means that the fluid elements themselves have got a rotation associated with them. Now, for 100 years or so, we've studied what I would consider to be a simplified form of turbulence. So that would be homogeneous turbulence. Now, what do I mean by homogeneous? Homogeneous means that essentially its properties don't vary. They remain the same wherever you are. So they don't vary in space. Another thing we consider is that the turbulence is isotropic. That tells us that it doesn't matter which direction we look in, the turbulence remains the same, depending on what direction. And as an aside, the isotropic approximation is quite reasonable for small scales. So, for example, if you were stood in this weather centre in North Yorkshire somewhere, you might see rain in every direction. But because of the nature of the frontal rain that advects in from the Atlantic, actually at large scales, we have a sort of strong preference, I suppose, for north-south systems, which means that we can't really describe turbulence as being isotropic even at large scales. But the problem is that turbulence has edges, or fronts, as we say as I refer to it in the title of the talk. So here are some pictures that come from our laboratory, and you can see very clearly there's a sharp edge between the turbulence and the background. And I'm going to talk about two applications later on in the lecture, wind farms and clouds. And in both cases, you can see very clearly there's an edge to the turbulent wake produced by the individual turbines, but also there's a very distinct edge at the edge of the cloud. Okay, the cloud doesn't just gradually transition from cloud to sky, there's a very sharp and distinct edge at the edge of the cloud. And these turbulent interfaces are the subject of this lecture. So let's build this down into the simplest possible building block that we can, and that would be where I have a turbulent flow. And as I reminded you, a turbulent flow has vorticity, so we have non-zero vorticity within the turbulence. And I'm going to surround it with a non-turbulent background, so a background that has zero vorticity. Now, in these circumstances, we can say that the very edge of the turbulence must be a surface of zero vorticity, because, of course, I go from 0 to some non-zero value within the turbulent flow itself. We can write out the transport equation for vorticity, and we can write it along that surface, and it tells us that the only source term that exists in this scenario is going to be viscous diffusion. Now, all of you will be familiar with viscosity. So, for example, when you pour honey, it's quite sticky. Now, all fluids are viscous. It's just some are more viscous than others. So, for example, honey is very viscous in comparison to air. But the important thing is air is still viscous as well. Now, the physics of viscosity are that they only matter at the very smallest scales of the turbulence. And so, as a result, the interface is thin, and we see this sharp transition between the turbulent flow and the background. Now, another thing that you'll all be familiar with is the fact that turbulent flows grow with distance. So I've marked onto this slide here that we can see that as I move further downstream, the size of the turbulence is physically getting larger. Now, that must mean there's be a transport somehow of fluid from the background into the turbulent flow itself. And of course, that transport must cross the interface which separates the turbulence from the background. And collectively, these processes are known as entrainment, and that's something that I'm going to be speaking about quite extensively in this lecture. You will all no doubt be familiar with this idea of turbulent flows spreading by looking at, for example, chimneys or volcanic eruptions and things like this, where clearly we see that the turbulent flow spreads as I move downstream. Now, that would be what I would describe as the special case, or maybe the simplest possible example of a turbulent interface. But in general, a turbulent flow is embedded into a background which is also turbulent. And in these circumstances, we've got non-zero vorticity on both sides of the interface. And our research group, we've really taken on a lead in trying to understand the physics of what's going on in these turbulent interfaces. And in fact, we were, a few years ago, the first group to definitively show the existence of these interfaces, when as recently as 2014, it had been suggested that they may not even exist in certain circumstances. And if we go back to our volcanic plume example, this is in fact an example of a turbulent interface, because the volcanic plume is erupting into the turbulent atmospheric boundary layer. And so as we can see, I've got non-zero vorticity on both sides of the interface. And I've chosen this particular example because I think it very nicely illustrates the effects of external turbulence on the nature of the turbulent interface. Okay, so the question is, how do we go about studying turbulent entrainment and turbulent interfaces? Now, the short answer to this question is that we point lasers and cameras at things. So we use two primary techniques to do this. And the first one is called particle image velocimetry, or PIV for short. Now, PIV involves essentially seeding a flow with tracer particles. So think about, for example, dust particles in a dust storm, the sorts of particles that will allow you to visualize the flow of the air that's advecting these particles. And what we do is we use a laser and we illuminate a particular region of the flow, and we take pictures with a camera. We take 2 pictures in very rapid succession, and what we do then is we do some processing where we cross-correlate the images in order to understand how far have the particles advected in that time interval between the 2 images. After that, we can then do post-processing to calculate things that might be of interest to us when it comes to entrainment itself. So this is what a typical setup might look like. These are 2 high-speed cameras. What we're doing here is what's called a calibration experiment. So essentially, we're imaging an object of a known size so that we can convert pixels into millimeters, for example. And you can see the light sheet being introduced into the facility. The particular experiment we've got here is I have 2 different generators of turbulence. So I want to look at the interface where we get this interaction between these 2 streams of turbulence. So once we've captured the images, we somehow need to process them in order to capture a velocity field and then things that might be of interest to us. And so let's take a bit of a closer look at how that might work. So what I've got here is I've got actually 3 images from when I was a postdoc at University of Texas. And these are images taken in a Mark V supersonic boundary layer. And I've chosen them because I think even the images themselves give quite a nice indication of the presence of a turbulent interface. Essentially what happens is out here, the flow is very, very fast. So Mark V means 5 times the speed of sound. That means that the flow is extremely cold. In fact, it was sufficiently cold to liquidize oxygen within the stream. Whereas the wall, relatively speaking, is quite warm. And so therefore, the fluid close to the wall is slightly warmer. It therefore has a slightly reduced density. And therefore, we're able to get fewer seeding particles into this wall layer. So even the images themselves give us an indication that these interfaces are quite prevalent in aerodynamic flows. But what we do is we then take our particle image and we can divide it up into a grid of what we call interrogation windows. These might be, for example, 32 by 32 pixels or something like that, for example. Let's now focus on one of these interrogation windows, and let's take a look at what the 2 particle images might look like. So at some time instant t0, I might capture an image of particles that look like this. And then at some time instant later, t1, these particles have obviously advected, and so I capture an image of different particles. And of course, they've advected because the flow has advected them. So what we do is we take the particle images at time t0, which hopefully you can see as the gray dots, and we cross-correlate these particle images to those which we capture at time t1. And when we run this cross-correlation algorithm, we find that the most probable displacement from time t0 to t1 is the vector which describes the velocity in this particular region of the flow. So what we can do is we can do a simple calculation where I divide the displacement by the time to give myself a velocity. And once we do that, if we use a high-speed camera, we can capture data sets like this, which shows the vorticity field in the wake of a model wind turbine, where we can see turbulence both generated by the wind turbine itself and also turbulence in the free stream. Okay, so that's the first technique that we use, and then we typically combine this with a second technique to measure scalar, excuse me, and this is a technique known as planar laser-induced fluorescence. Essentially, what we do is we introduce a dye into the flow which fluoresces. That means it absorbs light at one wavelength and emits light at another wavelength. And essentially what we do is we just capture this fluorescence using our camera. And so here is an example where we seed scalar into the wake of this small object. And what you can see is at some point there's a very rapid transfer as this scalar is entrained from the wake of the small object into the wake of the larger object. Now what we do in order to measure entrainment is we actually combine both of these techniques. So here is a raw image which shows a combined PIV and PLIF experiment for a model wind turbine wake. And what you can see is that the laser light that we use is green, and so the light which is scattered from the particles is green, but the fluorescence which comes from our scalar is yellow, and so we can distinguish between the yellow light and the green light with our different cameras. So here is an example of the kind of setup that we might create. So we generate turbulence with some kind of turbulence generating grid. I might then place an object into that stream of turbulence in order to generate my primary turbulent flow. In this case, we can use a simple cylinder, for example. And then I'm able to image the fluorescence using my PLIF camera. And of course, we know that the PLIF is going to yield yellow light, so I can put a yellow filter onto the camera. And I can put a green filter onto the PIV cameras so that I can simultaneously capture both velocity and scalar at the same time. So this illustrates essentially the process of how we might go about extracting interface information. So we might, from our PLIF image, be able to extract the location of the interface, which is this red line. We can then overlay the interface position onto our PIV grid. And finally, we can produce now an example of where I have an interface which has been identified using the scalar and a vorticity field which has been captured using my PIV. Once we've done that, we then need to be able to calculate things which are going to be of interest to us. And of course, that means we might want to calculate the rate of entrainment, for example. So how do we go about doing that? Well, we can capture, as I say, our interface using a PLIF experiment. I can then identify the location of my interface at time t0 in my time series of data. I can then look at the next interface location in my time series, so at time t1, and this is the blue line that we've managed to identify. And at the same time, from my PIV data, I can extract the fluid velocity, which are these green arrows. What I can then do is I can advect my interface at time t1 backwards in time by the fluid velocity which I've measured in the PIV. And of course, we can see that these two interfaces do not overlap with one another. And the reason they do not overlap with one another is because in that time difference, entrainment has taken place. And so if I capture the relative motion of these two interfaces to one another, we're able to capture essentially how much entrainment has taken place in that very, very short time window between the two records in my time series. And there's a really important observation to make here that the majority of the data points show that my interface has moved out in this time period delta t, which means that there's been entrainment that has taken place in that time interval. But you will see that there are some vectors pointing the other direction, which means that this process of entrainment is bidirectional. I can essentially entrain background fluid, but I can also detrain fluid, which is where fluid will be transported from the wake into the background. On average, of course, we expect there to be more entrainment because my flow is growing, but that doesn't mean that on an instantaneous case, we do see a unidirectional flow. Okay, so these are the sort of methodologies that we adopt. Now let's take a look at some of the results that we've made, that we've achieved over the years. And first of all, let's look at some sort of fundamental scientific advances. So that one of the first things we're able to show is that the physics of turbulent interfaces are different to the physics of turbulent, non-turbulent interfaces. With turbulent, non-turbulent interfaces, we identified that the dominant physics is viscosity. So essentially, if I have a rotational fluid element immediately next to an irrotational one, it's only through this essentially transmission of rotation through the viscous diffusion that the entrainment is able to take place. But when I have background turbulence, this is in fact negligible. And we've shown that there's an alternative mechanism which is based on inertia. Essentially, the interface acts like a kind of barrier. And so if I'm one of these sorts of vortical structures which is existing immediately under the interface kind of pushes down on this vortical structure, which gives us some kind of strain direction, illustrated by these red arrows here. And of course, if the vorticity somehow aligns itself such that this straining squeezes it out in this particular direction, then what happens is we have, by a process which is known as the conservation of angular momentum, I'm able to increase the rate of rotation in exactly the same fashion that a figure skater is able to do so when they reduce their characteristic length scale by moving their arms in whilst doing a rotation for a spin. So essentially, if I take the rate of rotation, which I've called omega 1 here, and I multiply it by this characteristic length scale, this is preserved. And so if I reduce the length scale because of the squashing motion that is taking place in the interface, I increase the rate of rotation in exactly the same fashion as this figure skater. So this is a much more complicated mechanism than a simple viscous diffusion mechanism, and that has some serious connotations when it comes to modeling the spreading of these sorts of wakes. We'll come on to this a bit later when we talk about wind turbines, for example. We've also shown that turbulence tends to make these interfaces rougher and more contorted. So in this slide, we've got three figures. One figure where I've got a wake with zero background turbulence, a wake here where I have moderate free stream turbulence, and then a wake here where I have a much more intense form of free stream turbulence. And what we've been able to show is that as I increase the level of the free stream turbulence, this interface becomes much more corrugated, it becomes much rougher. And of course, a rougher interface means that I have a larger surface area, and a larger surface area means that there's more opportunity for these transfers that take place, i.e. for this entrainment to take place. We've then taken a look at the nature of the entrainment into a turbulent wake. And one of the things that we've shown is that in the near wake, for example, so in this region of my wake, we see an enhanced entrainment rate. So essentially, I'm trying to indicate this through the sort of spreading rate that we have of the wake. And of course, this seems intuitive because if I have more interface over which a mass transfer can take place, then I might expect that I might entrain more fluid into my turbulent wake. But perhaps counterintuitively, we've shown in the far wake, we see a reduced entrainment rate. And this goes back to one of the points I made slightly earlier, that entrainment is in fact a two-directional activity. Simultaneously, I have both entrainment, in which fluid is transported from the wake from the background into the wake, and that coexists with the opposite, which is detrainment. And what we find is in the far wake, this detrainment starts to take over. And so actually the presence of free stream turbulence can suppress the growth rate for these wakes. Something, again, that becomes important when it comes to modeling wakes in applications like wind turbines, for example. Now, a wake is a region where I have essentially a reduced speed of air or a reduced momentum. And what happens is a wake obviously expands because we entrain background fluid into the wake. But at the same time, the velocity in the wake, or the speed in the wake, also increases because I'm going to drag with me fast fluid into this slow-moving fluid. And of course, when I mix in the fast fluid to the slow fluid, eventually I manage to speed things up. So as I move further and further downstream, eventually this wake will disappear. Now, one of the things that we were able to show is that if I look at the rate at which momentum is entrained into the wake, it has a very, very distinct what we call efficiency, which is essentially the ratio of how much mass is entrained into the wake versus how much momentum is entrained into the wake. What this tells us, if I know how much mass is entrained into the wake, then I can exactly predict how much momentum is going to be entrained into the wake, because I know what this free stream velocity is going to be. What we've shown is that this is no longer the case when I have a turbulent background and I have a turbulent-turbulent interface. We instead see that an additional term exists, which means that I don't necessarily automatically know how much momentum is going to be entrained into the wake if I know what the mass flux is going to be. And again, this has consequences when it comes to modeling wind turbine wakes, as we shall see very, very shortly. So these are some of the fundamental scientific advances we've made, but let's take a look at how this applies to two particular applications. So first of all, we're going to look at wind farms. So here is a picture of a wind farm, and as you can see, these individual turbines produce wakes. These are very nicely visualized if the atmospheric conditions are right. And so here is what a turbulent wake downstream of a wind turbine might look like. So as we've discussed, this wake is going to grow, and this wake grows because, of course, we entrain background fluid into the wake. And what we see is, in the wake, we have essentially slow-moving fluid, because my turbine is extracting kinetic energy from the wind. Therefore, the wind downstream of the turbine slows down. But this slower-moving fluid essentially starts to become faster and faster and faster as we entrain faster-moving air into the wind farm. So eventually, this, what's known as a velocity deficit, starts to reduce as I move downstream. Basically, the speed in the wake gets faster and faster and faster the further I go away from the wind turbine. And that's due to entrainment. Now, what are the consequences of this in a wind farm? Well, really, there are two major consequences. One is, if I situate a wind turbine here in a flux of slow-moving air, clearly I'm not going to be able to extract anywhere near as much power as if I stick my wind turbine in the fast-moving air. So we see centrally located wind turbines generating much, much electricity than the turbines on the front row of the grid. Now, all of you have presumably flown in an aeroplane through turbulence, and you'll recall that it's quite a bumpy ride. And so a bumpy ride means that the blades of the turbines essentially get bumped around a little bit by the presence of this unsteady flow. And that accelerates something called fatigue. So you've probably been familiar with the idea of taking a paperclip, and if I bend this paperclip repeatedly, eventually this paperclip is going to break, and it breaks through fatigue failure. And so if I expose a wind turbine to a turbulent wake, we're going to accelerate fatigue failure, and indeed this is a common cause of failure for example, the gearbox and blades on wind turbines. So when it comes to designing a wind farm, we obviously need to know something about how these wakes are going to spread so that I can arrange the turbines in a way that firstly minimizes the amount of fatigue damage I'm going to experience, so I reduce my maintenance costs, but also ensures that I'm able to maximize the amount of power that I can produce, all constrained under the total amount of land that I can build my wind farm on. So this optimization can't be done without knowledge about the spreading of these turbine wakes. So let's take a bit of a closer look at this, about how important this is going to be when it comes to things like siting wind turbines. And let's imagine I'm able to come up with some array of turbines like this. We might want to know how important are these velocity deficits that we're talking about. So for those of you that have ever studied aerodynamics, you'll know that the main aerodynamic force on a body is called the drag. And the drag force increases with the square of the wind speed, so this u squared term. Now, a power is essentially a force times a velocity, and so if I multiply this quantity by another u, I end up with a u cubed. This tells me essentially that the power I can produce from a wind turbine is going to scale with the cube of the velocity, which makes it extremely important. Because if we put in some example numbers, a 20% reduction in the wind speed, because I have a turbine situated in the wake of an upstream one, leads to a 49% reduction in the amount of power that we can produce. So essentially, I reduce the wind speed by a fifth, I reduce the power by a half. This is a pretty substantial reduction in power production. So at this point in the talk, I'm going to go for some audience participation, and given what we've learnt so far about the nature of the power that we can produce due to the spreading of turbine wakes, I'm going to ask you to vote which of these two wind farms do you think is going to generate the most power. So the first wind farm on the top has 7 wind turbines, which I've spaced reasonably close together so that they have a 20% velocity deficit, versus this bottom wind farm in which I have 5 wind turbines spread further apart, so the wake has had time to recover, and as a result, these turbines are only seeing a 10% velocity deficit. So who thinks that farm 1 will generate the most power? Raise your hand. Who thinks farm 2 will generate the most power? Okay, let's do the maths. So wind farm 1, I have 6 wind turbines here, which are seeing 80% of the wind speed, and I have a 7th wind turbine here, which is seeing 100% of the wind speed, such that I'm generating about 4 times the power of a wind turbine in isolation. Well, this is pretty hopeless if you think about it. I've bought 7 wind turbines, and yet I'm only producing the same amount of power as if I'd bought 4. In wind farm 2, we have 4 turbines seeing 90% of the wind speed, and the 5th turbine seeing the full wind speed, which means that I'm afraid you're all wrong. Wind farm 1 was, in fact, the wind farm that generates the most power. Now, there are 2 lessons to be learned from this. 1, never trust an academic in an inaugural lecture. And 2, which wind farm would we actually build? We would build wind farm 2 because A, I only need to build 5 wind turbines as opposed to 7 wind turbines, and B, my maintenance costs are going to be substantially reduced. So power isn't everything. Okay, we've also got to think of the finance and the economics as well. Okay, so what kind of research have we done specific to wind turbines? Well, we did some very cool experiments with our collaborators in Germany, in the University of Oldenburg, where we've placed a reasonably large model wind turbine into their highly specialized atmospheric wind tunnel. Now, this wind tunnel has what's called an active turbulence generating grid in it. So this grid has 81 independently controlled motors and flaps, which means that they can generate turbulence of all different varieties within the wind tunnel. In fact, they can put an anemometer on the roof of the building and exactly recreate that turbulence in the wind tunnel. Very, very impressive. And what we've done is we've looked at how do these wind turbine wakes spread in response to different types of turbulence, how do they spread in response to different operating conditions for the wind turbine within the tunnel itself. Secondly, we've also looked at the multi-scale nature of wind turbine wakes. Now, wind turbine wakes are quite complicated flows. We have various types of sort of coherent motion that coexist. So, for example, we have this kind of helical vortex, which is produced by the tips of the blades. We have some sort of structures introduced by the nacelle of the turbine. And if we go further downstream, the whole wake starts to sort of meander in a sort of large, slow process like this. And what we've done is we've developed techniques whereby we can take our experimental data and we can extract these various modes that coexist within a wind turbine wake. So we can find, for example, the tip vortex system, we can find the wake meandering system, and then we've developed the mathematical framework that enables us to track the energy exchanges that take place that yield these particular coherent motions and that give us the sort of rich dynamics that exist within a wind turbine wake. More recently, we've taken some techniques from colleagues that are looking at structural health monitoring for aircraft, and we've implemented them into our wind tunnel and our water facility so that we can, in real time, measure the fluctuating strain in wind turbine components. I told you that one of the issues with a turbulent flow is, of course, that we can accelerate fatigue damage. So we might want to know something about how does a particular turbulent flow translate itself into the mechanical response of the turbine blades itself. So essentially what we've done is we've taken fiber optics, which we embed onto the surface of our structure. In this case, the structure is just a simple cylinder. And that gives us the fluctuating strain that exists within the cylinder, which is a good metric essentially for looking at the loads that are in the cylinder. And we can couple that to time-resolved PIV as well, so we can try and relate structures in the flow field that initiate particular responses in the cylinder themselves. We've now implemented this in our large wind tunnel, where we can see here in this particular wind turbine model, you can see this turbine blade here is implemented with these fiber optics that enable us to capture the strain. And what we can do is we can vary the spacing of these two wind turbines to try and better understand how does the positioning of these two turbines translate into strains that exist within the blades. Now, on a windy day, if you were to walk into a forest, you would probably find yourself somewhat shielded from the wind, and that's because the forest essentially presents a blockage to the flow, and a wind farm is no different. If I have a very large assortment of turbines, these present quite a considerable blockage to the flow, and as a result, the configuration of the turbines affects how much of the flow is, for example, passed over or around the wind farm. And so we're now doing some experiments as well where we get different configurations of wind farms. Here we're essentially modeling wind turbines with porous discs, which actually give us a reasonably good representation of a wind turbine wake. And we're able to try and understand what kind of arrays of discs give us the most efficient power output. And indeed, we can study the interface that exists between this, essentially this wind farm layer and the free atmosphere as well. And more recently, we're applying our work on turbulent interfaces to clouds. And before we consider clouds, I think maybe a small crash course on how clouds work and how turbulence is important in clouds. So clouds are quite complicated things to study, but essentially they work as follows. Everything starts really with the sun. So the sun essentially heats the ground. So the ground starts to warm. And as a result, warmer air starts to travel upwards because, of course, warm air is lighter than cold air. And, of course, what we have in this layer here is we have humid air. So essentially, we start to transport humid air up into the higher reaches of the atmosphere. Now, the atmosphere contains tiny particles of dust and other things above the sea. This could be salt, for example. And so eventually, if I'm able to transport the water to an altitude where the temperature and pressure is low enough, then water will condense onto these particles, and these particles are what are known as cloud condensation nuclei. And this is a purely thermodynamic process. So essentially, the water just comes out of its vapor form and condenses onto these particles. This obviously then forms a cloud, but the story doesn't end there, because all sorts of things are going on in a cloud. One of the most important things, of course, is at the top of the cloud looks out into space, and of course the cloud is much warmer than space, and so therefore the cloud radiates into space, which can generate cooling in the top of the cloud. So this can generate a sort of convective cycle that happens within the cloud, and that can trigger turbulence. So the cloud becomes quite a turbulent environment. And of course, if I have a turbulent environment, that means that I have entrainment going on in which background dry air is entrained into my cloud, which subsequently affects the turbulence and the thermodynamics and things like this. Now, I mentioned that the formation of these droplets is a thermodynamic process, but the problem is that thermodynamics is pretty slow, and in fact, it's far too slow in order to explain things like rainfall. So there must be additional mechanisms that are going on in the cloud. And of course, the additional mechanisms are the turbulence. And of course, what happens is the turbulence advects the droplets, and some of these droplets will collide with one another. And of course, if two water droplets collide, they will coalesce in order to form a larger droplet. And eventually, if my droplets become large enough, then they can fall out of the cloud as rain. So the question is, how does entrainment and interfaces and all this sort of thing affect rainfall formation in clouds? And so that's what we're working on at the moment. So clouds are environments at an extremely high Reynolds number. Now, without wanting to get sort of into the details of this, this means that we have something that is a very intermittent environment. Now, what do I mean by intermittent? Well, I mean that not much is going on, and then bang, suddenly I get a big spike, and then not much is going on. And so the structure of a cloud might look a little bit something like this, where I have little bubbles of turbulence where not a huge amount is going on, but these little bubbles are separated by interfaces where I get very, very strong local strain rates. I get very, very powerful turbulent events that take place in these little interfaces. Now, when a droplet crosses a region of the flow like this, we can get extremely high accelerations. So this is data for a droplet in high Reynolds number turbulence, so very similar to what we see in a cloud. And I don't know if you can read the scale, but what we've got here is we've got the acceleration of the droplet. And if we look at this region here, you can see that this region is in yellow. And if you're able to read off that scale, this is an acceleration in excess of 1,000 g, where g is the acceleration due to gravity. To put that into some sort of context, a highly trained fighter pilot in a specialist equipment like a G-suit is considered to black out at about 10 g, and a car crash of around 75 g is considered to be fatal. So you really, really wouldn't want to be a droplet in a cloud. Okay? They experience some extremely high accelerations. So what we want to do is we want to try and understand how this sort of turbulence intermittency affects things like collision between droplets and therefore rainfall, as well as what about the exchange of dry air with moist air at the cloud edge through things like entrainment. So the first sort of part of the work package is really a sort of continuation of what we looked at previously. So if you recall, previously we looked at entrainment of things other than mass. So we looked at the entrainment of momentum. Now in a cloud, we also have buoyancy and energy. So buoyancy is essentially what drives this sort of convection that we have in a cloud cycle. And what we want to do is we want to try and see how does the fact that I'm entraining from a turbulent background affect the rate at which buoyancy is entrained. Because as I say, buoyancy is an extremely important part of the physics of what's going on in clouds. And then the final aspect of what we want to look at is we want to look at the dynamics of the droplets themselves, in particular when these droplets cross these kinds of interfacial regions. And we do that by considering this monstrosity. So this is the equation that governs the dynamics of droplets in turbulence. And probably one thing you will notice is that it is long and painful. And so as a result, almost always it's reduced to these two terms here. Now, for those of you that have done some maths, mechanics, or anything like that, all we've got here is I've got mass times acceleration, and here I've got two forces. So this force is gravity, so essentially just the gravity acting on the droplet, and this force here is what's known as the Stokes drag, which is the same drag as we might experience if I was to put, for example, a ball bearing in a tube of honey, for example. So this is the viscous force imparted on the droplet. What we're going to be looking at is we're going to be looking at this term in red, and without going into the details, the only thing I really want you to focus on is this thing here, which is essentially what's called a time history. So what this tells me is that if two particles have two different time histories from one another, they will experience a different force. Now this is important because these two, what I would call classical terms, so the gravity and the Stokes drag, are identical for two droplets of the same size, which means these two droplets of the same size would fall at the same speed, meaning it's very difficult for these droplets to collide with one another. If, however, these droplets have experienced a different time history, I now have a mechanism which can bring these two droplets together such that we can get collisions between droplets of the same size. So we're going to be exploring the importance of this term, and we're also going to be exploring the validity of this equation, because actually under certain circumstances, I think this equation is no longer going to be valid in these particularly complicated regions. We want to try and see, is there something else that we can come up with instead to describe the motion of these particles as they cross those interfaces. So given the time and the look on my chairman's face, I'm going to reach my sort of summary and outlook. So I guess the most important thing to say is that things aren't all quiet on the turbulent front. I would argue there are some pretty interesting physics that take place in turbulent interfaces. And it's quite something really to think about that these very thin layers, typically only a few millimeters in thickness, play such an important role in some really important applications. So, for example, energy harvest and cloud microphysics. And by extension from cloud microphysics, weather and even climate dynamics. But, of course, there is still much to do, in case there are any funders in the audience. We haven't answered the zeroth order question, so I still haven't given you a definition of what is a turbulent interface. And there are various other turbulent interfaces that we want to consider. So, for example, the air-sea interface, where it is assumed that between 25 and 30% of man-made carbon dioxide crosses this interface. And, of course, that is a very important problem for us to be considering. What is the role of turbulence in the air-sea interface, and indeed other interfaces that might exist in the ocean because of things like salinity concentrations and things like that. So, that's the end of the scientific part of the talk. But now really for the important part of the talk, which is the thank yous. So science is a collaborative endeavor, and really the work that I've presented here is not my work at all. This is the work of the incredibly talented PhD students and postdocs that I've had the pleasure to work with. I've managed to lead a sort of guiding hand every now and again, but really this work is theirs. So I can see many of them in the audience today, so thank you. Thank you for your efforts, and also thank you for making it such a fantastic working environment. I've enjoyed every minute of it. I'd also like to thank colleagues both at Imperial that I've collaborated with and beyond. Scientific collaboration really is what makes the world go round. I think a particular thanks to Professor Ferry Ali-Abadi, who was the head of department that hired me in the first place. So hired me aged 28 when I didn't really know what I was doing, and don't know why he hired me, but thank you very much. Really appreciate it. And also to my PhD supervisor, Bharat. And really, without Bharat's guidance, none of this would ever have got off the ground. I, in fact, started my PhD on a completely different topic and ended up studying turbulence purely by accident. And this was very serendipitous because I've obviously, A, made a career out of it, but B, I genuinely fell in love with it. And Bharat, you're incredibly supportive of that transition, and so thank you very much. And been supportive all the way throughout my career as well. So thank you. Obviously, there's no such thing as science. There's no such thing as science without funders. And so I'd like to thank all of these funders. And so indirectly, that means you, because I think probably about 90% of my research funding has come from the taxpayer. So thank you very much. And primarily to troll my dad, who sat there in the front row, a particular thanks to Boris Johnson. Because when my cloud project was funded, we were in that sort of intermediate period between Brexit and the UK rejoining Horizons Europe. And as a result of the sort of quirks of how the funding went in those days, I got a windfall of around £250,000, which for those of you that work in finance is nothing, but for us academics is an enormous amount of money. So thank you very much, Boris. Then I'd like to thank all of my colleagues at Imperial. So, of course, I've listed my collaborators from a scientific perspective, but of course there's no such thing as science from an experimental perspective without technical assistance. So thank you to all of the technicians who have done such a fantastic job of putting our experiments together and keeping the show on the road. Thank you to the administrative staff for making everything run so smoothly. And thank you to all of my colleagues with whom I don't have scientific collaborations, but that make Imperial such a fun and spectacular place to work. So thank you to all of you. Thank you to all of you for attending this lecture. It really means a lot to me that you've made the effort to come this far. And there is a drinks reception as well, so make sure you make the most of that afterwards, because there are very few perks we get as academics. This drinks reception is one of them. That leads me on to my first apology, which is to my turbulence and turbulence modelling students, and I have seen a few of you in the audience. Depending on how well the drinks reception goes, I might not be at my best at tomorrow's 9 a.m. lecture. Thank you also to my friends and family. Honestly, without friendship and support from those closest to you, none of this really makes any difference to anything, so thank you all so much. Some of you have travelled from an extremely long way, so thank you in particular to my sister who's travelled from Pakistan to come to the lecture. And a huge thank you to my parents. I mean, I sort of went to university at 18 and I never left. And at no point did you ever complain at me or tell me to get a real job. So thank you very much. And then finally, and most importantly of all, goes to my amazing wife, Becca. I'll simply say this, that by some pure chance coincidence. Today is literally exactly the 10-year anniversary of us first meeting. And I think the fact that she sat here in a lecture theatre listening to me drone on about turbulence rather than being literally anywhere else more romantic speaks volumes about how incredibly supportive you've been. So thank you so much. And with that, I'm happy to take questions.
That was a fantastic one. My name is there for no reason because it's all your show today. Any questions for Oliver? Professor Buxton, sorry. Please. You have a microphone there, Sarah.
Back in the wind farm modelling,
Yeah.
I was wondering, in looking at the maths and conclusions that came out of that, as to whether you'd looked at the impact of the different lengths of turbine blades and what that might have done to your calculations.
I mean, yes, so it's actually a very good question, surprisingly so. So for example, we showed you some, I showed you some illustrative examples from the experiments we did in Germany, where we had the active turbulence generating grid, and there are some lines on a graph, and some of those lines were related to something which is called the thrust coefficient, and the thrust coefficient is essentially something which characterizes the aerodynamic performance of the turbine. And there are various ways that you can adjust the thrust coefficient of a turbine. One of them is by adjusting, for example, the angle of attack on the blades, but another one, of course, is by adjusting the aerodynamic design of the blades themselves. So by looking at different thrust coefficients, we were able to, in some sense, look at the effect of aerodynamics. But what we haven't done is we haven't looked specifically at varying the sizes of blades within the same wind farm, for example, which is something I've not seen wind farm developers do, where you might have a combination of big and small turbines. Generally, they tend to be the same size. But yes, it's actually a very interesting idea.
There you go. Any other questions for Oliver? One in the back.
Going back to the cloud equation for the forces on a droplet, how can the force be a function of something, its state in time gone before? Okay,
so if I have an object, I produce effectively a viscous induced boundary layer on the object. Now, if I'm sort of moving this object at a sort of constant speed, then essentially some equilibrium forms between the nature of the boundary layer that develops on the object and the speed at which I'm dragging the object. But if I then accelerate the object, for example, then what happens is my object might start moving at a different speed, but the viscous boundary layer is effectively still a viscous boundary layer which was formed at the previous speed. So essentially there's some kind of time lag between when I start the acceleration of the object and when the viscous boundary layer adapts. And so what happens is it takes some time for this new equilibrium to be restored, and this is essentially the origin of what's called the Bassett history force. So it's a viscous force which is due to essentially this kind of acceleration that takes place in a viscous environment.
So the viscous boundary layer almost has like an inertia?
Well, usually we separate inertia from viscosity. So usually inertia we consider to be things which are reversible, whereas viscosity is irreversible.
Okay, thank you.
We have a question here, and then a question in the back. You want to start with this one here?
I was going to ask, in the next 10 to 20 years, if you could solve one thing that's currently unknown in turbulence, what would it be and why?
That's a very good question. So the thing that I'm probably most excited about is essentially the role of this history force in the droplets. And obviously I'm lucky enough that I've got an opportunity to do this because we now have PhD students and postdocs working on this. More generally, I think we have a collaboration now with the Met Office. And when it comes to actually making weather forecasts and climate forecasts and things like this, that equation is far too low level to be incorporated into any kind of forecast model. So the Met Office usually solves on a grid of order 10 kilometers, but these physics take place on order of millimeters. So essentially everything that we discover there, all of these interesting physics, are not going to be incorporated into a meteorological model. They will instead be parameterized somehow, and then these would then be input into a revised meteorological model. So in 10 years, I think the argument, the objective will be to understand the physics, to parameterize it, and then improve the accuracy of weather forecasting.
Thank you. One final question at the end.
Okay, brilliant talk. And it's about turbulence, which we don't really know the total answer to. And it's one of the great unsolved problems. I mean, we can go about in an engineering context and use averages and closure, but it doesn't really get to the heart of it. But I have read recently, admittedly, it's not the Daily Mail, but it's the New Scientist, which actually said that AI can help.
Yeah.
It can give you insights into the nature of the Navier-Stokes equation itself. But it claims that you can actually use AI to solve the Navier-Stokes equation, which I don't believe that you can do. But that's just me, right? I'm much more mathematical. But the fact is, can, and it's something that you can exploit and have greater insight than I do, to help improve the situation, give you greater insight. Is that real? Is the Daily, not the Daily Mail, but the New Scientist?
So I agree with you that AI might not necessarily be able to directly solve Navier-Stokes, but it can be used for example, I've seen people use this an AI approach to solve sort of Poisson equation for pressure, for example. But more importantly, back to this, where I think AI is important is in let's say pattern recognition. So one of the pattern recognition. One of the things that we're interested in is, for example, what kind of features of the turbulent flow switches on the Bassett history force, for example. And of course, if I have millions and millions of particle trajectories, I, as an individual, can't trawl through millions and millions of trajectories and try and identify, oh, this seems to be the sort of flow feature that switches this thing on or not. And I think these are the sorts of examples where machine learning can be extremely useful, actually. So identifying the kinds of features that make the Bassett force important, and as a result, that can then help with the parameterization because we know when we need to switch it on and when we don't need to switch it on.
Okay. I think we need to stop here. We're a bit over time. Thank you again. Let's thank the speaker again for a fantastic presentation. So, and I'd like to invite Professor Bharat Ganapathy Suravani for the vote of thanks.
Okay. Can I just say that was a fantastic talk. I mean, I know he made it sound complicated, but I can tell you it's really, really difficult stuff. And the way he has done this work, that excellence, the technical acumen, it's unbelievable. And he's already done a good job of thanking a bunch of people. I just wanted to say thanks to the Imperial events team for putting on this show and making sure we are all here. And I, despite Southwestern Railway's best efforts, I was not going to be able to make it because I was stuck in a train somewhere outside Basingstoke for a long time. But I made it here. So, I mean, from my own perspective, I kind of have 3 different milestones, I think, that I share in my life with Ollie. And I think they are milestones for him as well. I'm hoping. Anyway, I'm going to say they are my milestones anyway. So the 3 milestones, the first one is, so I was a new academic and I was offered this job as a lecturer in the Department of Aeronautics at Imperial in 2006, July, something like this. And I was going to start in 2007, January. And somewhere around October, and I was still a postdoctoral researcher at Texas, Austin, I get an email from someone called Oliver, right? And then it said something like, well, I hear you're moving to Imperial, and I would like to do a PhD with you because what I'm really passionate about is supersonic flows. And I was initially taken aback because, first of all, I hadn't even started. I may not actually take this job. And secondly, supersonic flows. I don't even know what was available at Imperial College at the time, and in terms of facilities and so on. And I said, yeah, sure, that sounds great. Like, I'll be in Imperial in January. Why don't you come and have a visit, and we'll work out what you want to do. And he came and visited, and we figured out that there was a project to be done in supersonic flows. And then, then there he started his PhD, in October 2007. And we were very, very excited and enthusiastic about building a supersonic tunnel and getting it to work. And I was like really excited. Until 9 months later, the single piece of equipment which should not break, broke. And we had no money to fix it. And I would say that started a fantastic career in turbulence. Right? I mean, in some ways, I thank the head of department then for not fixing that piece of equipment so that you could actually, benefit from this career. So he was obviously my first PhD student, and it was a first PhD for him. So that was a major milestone for us. And my PhD advisor told me, doing research or doing well in academia is all about working with good people. And she also told me that, if you want to be successful, make sure you have a good first PhD student. Boy, I got lucky there. Right? So that was my first one. So my second milestone is Ollie was responsible for my first destination wedding in the UK. So turns out Ollie was getting married somewhere, I didn't know this place existed, called Shropshire, somewhere between England and Wales, and back and forth. As you drive through, it kept saying, welcome to Wales, welcome to England, welcome to Wales, welcome to England, as you keep driving through this thing. It even sort of rained on the wedding day, and it was still a fantastic event. And I'm sure this has got nothing to do with Ollie, and I'm sure it was all Rebecca. But I just want to say it was a great milestone for me, because I've never gone to a place, stayed there for a wedding. And in India, we just all in one place. This was a completely different experience for me. And then finally, the third milestone was only a few months back. I got an email saying, Professor Oliver Buxton, and that he's been made a professor in the Department of Aeronautics. And for me, he's my first PhD student to actually become a professor. And I know it's his achievement, but I'm going to claim it as mine anyway. Right? I almost feel, I know his parents are here, but I feel like an equally proud parent in the sense that I want to, and really, from his talk, you can see, the title says, it's all quiet on the turbulent front, but really it's not. There are so many things to do, and I think turbulence research is in really, really good hands with Ollie, and I wish him all the very best.
Thank you, Arat. We miss you. I would like just to close this event with fantastic words of Arat. There's drinks outside for people online. Thank you for attending this. We didn't have time for questions, I'm afraid, but we overran a bit. Thanks again. It was a pleasure to have you all here today.